Hello students, hope you are doing well. So today we are going to discuss about the reduction of glucose, mannose and fructose with sodium borohydride. Now why we have used sodium borohydride? Reduction of the glucose can be brought about by using any reducing agent, and reducing agents are selective. Various reducing agents gives various products, but if our intention is to get sorbitol, if our intention is to get sorbitol, then we have to use sodium borohydride. So sodium borohydride is a selective reducing agent. That means it brings about the reduction of the carbonyl group. It brings about the reduction of the carbonyl group. Where can you see the reduction carbonyl group present? Carbonyl group, you can see its presence in carboxylic acids. You can see its presence in acid chlorides. Esters are there, and carbonyl compounds like aldehydes and ketones. So this is sodium borohydride is a selective reducing agent which brings about the reduction of the specifically the carbonyl group. So this reducing agent is generally used when there is a polyfunctional group containing compound is there. So our sugars, that is the glucose, mannose and fructose, these are also containing they also come under the category of containing the polyfunctional groups. Polyfunctional groups means more than one functional groups are present here, but here generally see here this is a carbonyl group, this is a functional group, but here we are considering as a primary functional group, that is, or a principal functional group. More accurately we can use the word principal functional group, because the priority whenever the aldehyde group is present along with the hydroxyl groups, always the priority goes to the carbonyl group over here, right? So hydroxyl groups are, we are not going to give the priority over here when the carbonyl group is present, but overall we call this molecule as a polyfunctional group containing molecule. So that is why we are using sodium borohydride, because we want to retain all the hydroxyl groups as it is. We want to bring about only the reduction of the carbonyl group. As a result, we can get a sorbitol. So let us see what is a simple mechanism behind this. Not in detail, we are dealing with the mechanism. Now sodium borohydride, here if you see the dissociation, how it ionizes sodium, it is a metal, highly electropositive, so it donates both the electrons. As a result, boron gets a negative charge over here. Now the boron, it will have to neutralize this negative charge. As a result, it gives one hydrogen in the form of hydride and gets converted into the neutral form, that is boron hydride. As a result, what we have to remember over here is one molecule of sodium borohydride provides 4H minus, that is 4 hydrides. See over here, it has totally 4 hydrogens over here which can be donated or which can be released as H minus. So how many H minus one sodium borohydride molecule can donate? It can give 4H minus. Hence, with one molecule of sodium borohydride, 4 molecules of glucose can be reduced at a time, isn't it? So, to reduce one carbonyl group, we require only one hydride over here. So, 4 hydrides are present over here. So, at a time, 4 molecules of glucose can be reduced, but followed by hydrolysis, because we need one proton also. So we will see now where the hydride, that is H minus, is added and where the requirement of proton is there. So proton we get from, that is followed by hydrolysis, that is acidic water, a little amount of acid if we add in the water. So that is why we represent H3O plus, that is a little bit acidic this water is. So now let us come back to the glucose molecule. Now this is the carbonyl group. This is highly polar, C delta positive, and oxygen is delta negative. So as a result, what is going to happen over here? Once this pi bond breaks, this will become H plus, this will become C plus, that is a carbocation, and this one will become O minus. So what do we know here up from this side? We know that there is a hydride ion ready over here. So the moment C plus is formed, the hydride ion will attack on the C plus. As a result, we have added one hydrogen over here, isn't it? Then what happens? The moment O minus is generated over here, that is the negative charge is generated over here, the proton from the water over here, this gets protonated. The oxygen will get protonated and this will be converted into a hydroxyl group. So this is the way how the aldehyde group is getting reduced to primary alcohol. So this part will be nothing but the primary alcohol. Now I told you that in our previous one of the lectures that primary alcohol group will be represented as CH2OH. Secondary alcohol group will be represented as a CHOH, and tertiary alcoholic group will be represented as COH. Okay. So what did we come to know from here? That whenever aldehyde group we want to reduce, or any carbonyl group, we have to use one specific reducing agent, and this one is the best one which brings about the reduction of the carbonyl group. So as a result we got sorbitol. Suppose if we use some other reducing agent, then complete reduction will take place, so we won't get our desired product. So whatever product we want, accordingly we have to select the reducing agent. Now let us see for mannose. What is the difference between glucose and mannose? The only difference is at the second carbon atom, but we are not at all concerned here from the second till sixth carbon atom. We are not concerned here. So whatever the configuration is there on the rest of the carbons, we are not concerned here. We are only concerned with the carbonyl group over here. So carbonyl group is terminal over here. So the explanation is exactly same as that of glucose over here. So as soon as the C plus, the carbocation, is generated after the breaking of the pi bond, what happens immediately? The hydride will come and attack the C plus, and we will get the hydrogen over here. And the moment O minus negative charge is generated over here, so the oxygen gets protonated, that is the water, from the water the proton will come and attack on the oxygen. So as a result, what we are getting from mannose, we are getting the alcohol which is called as a sorbitol. So what happened here? The carbonyl group, it is present terminal, so only the first carbon atom is under play over here. From the second, third, fourth, fifth and sixth, there is no disturbance, there is no change at all. Now let us go to fructose over here. So fructose is different. Glucose and mannose, they both are aldoses, aldohexoses. So their mechanism or their process is exactly same. But there is a little difference between the aldoses and ketoses. In case of fructose, we have, or there is a carbonyl group present at the second position. So generally what do we know? This is a keto group over here. So we have to always remember the aldehyde groups will come always terminal, either at the first or at the last. These two are the terminals. But a keto group will never come at the terminals. It will come somewhere in between. Whatever the length of the chain is there, leaving the terminals, it can fix up itself in between anywhere. But here in case of fructose, it is proved or it is confirmed that the keto group is present at the second position. And how do we have to prove this keto group is present at the second position? We are going to take up in our future classes. That is, what is the evidence that the keto group is present only at second carbon? It can be present at third carbon, fourth carbon, fifth carbon also. But no, in case of fructose, the keto group is present only at the second carbon atom. That evidence we are going to take up in the next class. But now For now, what we have to remember, here there is a keto group at the second carbon atom. Okay. Now what happens here also the same thing. This is delta positive, this carbon, carbonyl carbon, and oxygen is delta negative. The moment the pi bond breaks, the carbocation is generated. Now what do we know about the carbocation? The carbocation is sp2 hybridized, that is it is planar. So the incoming hydride can attack from the left hand side as well as on the right hand side on the second carbon atom. Suppose the incoming hydride attacks on the left hand side and the proton will go and attack the oxygen atom, so hydroxyl group will be formed. So what did I tell you? Suppose if the hydride ions are attacking from the left hand side, then what happens? We will get the hydride, that is why I am showing in this color, that is the hydride has attacked from the left hand side and the OH will flip to the right hand side. So what do we get? If the hydride attacks from the left hand side, we will get a sorbitol. Now if it attacks from the right hand side over here, if it attacks from the right hand side, then we will get a mannitol. So what is very important to note over here is, in case of fructose, this carbon, the carbonyl carbon, is not a chiral center. This is not a stereo center. But after the addition of the hydride ion over here, immediately this carbon will become a stereo center. That means a new asymmetric center is generated. That means a new chiral center is generated over here. So as per the rule of stereochemistry, where the new chiral center is generated, I have highlighted only that part. Only this part I have highlighted. So whenever a new stereo center or new chiral center is generated, by default we will get two isomers. So here what are the two isomers? These are nothing but two isomeric alcohols we call. So what are those two isomeric alcohols? How do they differ? They differ in configuration only at the second carbon atom. Configuration means arrangement of atoms. So here only in the second carbon atom, when you compare any other carbon leaving the second carbon atom, exactly the configuration or the arrangement is same. So these two, that is the sorbitol and mannitol, by default are formed by the reduction of fructose, because the keto group is present at second position. Because it is present in between, a new asymmetric center is generated. As a result, we will get two isomeric alcohols, which one is called as the sorbitol and the other one is called as the mannitol. So what is we have to remember? When an aldehyde group is present, it is present always at the terminal. Can we say that this is a stereo center? Here hydrogen is same. So this one is not a stereo center. That is, a new asymmetric center is not generated. When we reduce glucose and mannose, a new asymmetric center is not generated. That is why we get only a single product here. Glucose gives a single product as sorbitol. Mannose gives a single product as mannitol. But whereas in case of fructose, the keto group is present at the second position. As a result, here if you see, this is one different group, this is one different group. From here till here, this one will be considered as one different group and this one is a different group. So definitely this part is a new chiral center. So whenever a new chiral center is generated, as per the rule, we know very well, that is the isomeric product. Whatever product is forming, a alcohol is forming, two isomeric alcohols we will get. If a cyanohydrin is forming, we are getting two isomeric cyanohydrin. So like this we are getting over here. So you have to remember, when aldehydes are reduced, stereo center is not generated, new stereo center is not generated. But when a keto group is reduced, in case of fructose, a new stereo center is generated and we will get a mixture of the two isomeric alcohols. One is sorbitol and the other is mannitol. Hope this reaction is very clear to you. That is the reduction of the glucose, fructose and mannose by using sodium borohydride. Now you go practice today's lesson. But before you leave, don't forget to subscribe my channel and hit that bell icon so that you get the notification every time I upload a new lecture. See you again in the next video.